Watch this simulation of a hyperscale data center. A single node fails, emitting an anomalous pulse that aggressively duplicates, rapidly turning the routing fabric dark. To prevent this type of cascading collapse, modern communications infrastructure relies on the uncompromising management of strict logical and physical boundaries. The first of these boundaries is historical, the physical collision domain. In early networks, overlapping electrical signals on a shared wire physically destroyed data in transit. The second boundary is logical, the broadcast domain. Foundational discovery protocols require sending messages to every single connected network node, and this background noise must be strictly contained before it exhausts the processing cycles of the receiving hardware. While a signal collision is a tangible limitation of copper wiring, a broadcast storm is a vulnerability inherent to the stateless routing protocols themselves. As enterprise networks scale from dozens of local computers to hundreds of thousands of cloud instances, containing the blast radius of these domains becomes an existential requirement. The engineering history of networking is an ongoing effort to deprecate implicit protocol trust, replacing unconstrained data flooding with software-defined precision. Understanding modern zero-trust architecture requires first examining the raw physics of how data collides and recognizing exactly why legacy networks were designed to fail. Early network topologies relied on shared transmission media and centralized network hubs. These systems operated under a rigid half-duplex constraint. Network interface hardware could either transmit data or receive data at any given instant, but it could never perform both actions simultaneously. This chart illustrates a physical network collision. When two nodes attempt to transmit on a shared medium at the exact same moment, their electrical signals overlap. The combined voltage spikes violently above standardized allowable limits. Receiving network controllers continuously monitor the wire for these abnormal voltage changes. Upon detecting the spike, the hardware instantly rejects the corrupted payload, categorizing it as a runt frame. To handle this, half-duplex Ethernet utilizes carrier sense multiple access with collision detection, or CSMA-CD. Upon detecting the collision, transmitting devices immediately abort their payload and issue a specialized 32-bit jam signal, artificially extending the collision state to guarantee the corrupted frame is globally discarded. This visual shows the recovery calculation, a truncated binary exponential backoff algorithm. Devices calculate a random delay period before retransmitting. With every successive collision, the potential wait time expands exponentially. To prevent infinite latency during high congestion, the IEEE 802.3 standard explicitly caps this mathematical delay at 1023 slot times. While wired networks eventually evolved past this, wireless local area networks remain anchored to a shared half-duplex medium, the open radio frequency spectrum. Implementing collision detection here is physically impossible because an outbound radio transmission completely overwhelms weak incoming signals. This spatial map demonstrates the hidden node problem. Two devices sit well within range of the central access point, but physical distance or environmental obstacles prevent them from hearing each other. They both sense a clear channel and transmit simultaneously, causing a destructive blind collision at the access point. Wireless networks mitigate this using collision avoidance, executing virtual carrier sensing via a request-to-send, clear-to-send handshake. A node sends a tiny RTS frame. If the channel is clear, the access point broadcasts a CTS frame containing a microsecond duration value, explicitly instructing all hidden nodes to halt their traffic. Whether managing overlapping copper voltages or mediating the RF spectrum, shared mediums force hardware to waste critical milliseconds waiting in line. Scaling the enterprise required a hardware revolution. That revolution arrived with the standardization of full-duplex communication. By utilizing separate, dedicated transmit and receive channels over twisted pair copper or fiber optic media, traffic flows in both directions simultaneously, physically eliminating signal overlap. This technological shift gave rise to the modern Layer 2 switch, which allocates a unique, isolated collision domain to every physical port through a process known as micro-segmentation. While physical collisions were eradicated, a logical challenge took their place. By default, an interconnected switched fabric operates as a single contiguous broadcast domain. Broadcast traffic is a functional requirement for IPv4 protocols like ARP and DHCP. These protocols rely on sending messages to every connected node to map addresses and discover network services. When a switch receives a frame with a destination MAC address of all Fs, its operating logic forces it to flood that frame out of all other ports. Every connected device, from a high-end server to a low-power sensor, must interrupt its CPU to process the payload. The absolute boundary for this noise is a Layer 3 device. Routers and Layer 3 switches explicitly drop Layer 2 broadcast frames by default, containing the noise within discrete, isolated subnetworks. Enterprise architectural guidelines dictate a limit of 250 to 500 hosts, equivalent to a standard/24 subnet, per broadcast domain. Architects restrict domain sizes to create strict bulkheads for containing network anomalies, as modern hardware easily manages standard background broadcast rates. When the logical topology of these boundaries fails, the enterprise becomes exposed to catastrophic bridging loops. This animation highlights a fatal architectural flaw. A Layer 3 IP packet features a time-to-live counter that decrements at each hop until the packet is discarded. A Layer 2 Ethernet frame lacks a TTL mechanism. Caught circling a redundant switch loop, it circulates indefinitely, duplicating at every node. If a hardware anomaly, like a degraded fiber optic cable creating a unidirectional link, prevents a switch port from receiving bridge protocol data units, the spanning tree protocol assumes the primary link has failed. It erroneously transitions a blocked redundant port into a forwarding state, instantly triggering a broadcast storm. In June 2020, a fiber link failure in the Southeast United States triggered a localized routing issue for T-Mobile. Because the infrastructure failed to contain the anomalous traffic, a massive storm of device registration attempts escaped the local market and crippled national infrastructure, preventing tens of thousands of emergency 911 calls. To proactively suppress these storms, engineers deploy storm control at the access layer. They capture interface traffic over a 24-hour period to establish a mathematical baseline of normal broadcast packet percentages, then define thresholds that actively shut down anomalous ports. Beyond structural congestion, sweeping broadcast domains provide a target-rich environment for lateral east-west attacks. This flowchart illustrates ARP cache poisoning. Because the address resolution protocol operates without built-in authentication, an attacker can intercept an ARP broadcast request and inject a forged MAC address reply faster than the legitimate host. This establishes an adversary-in-the-middle position. All traffic intended for the default gateway is unknowingly redirected through the attacker's machine, exposing plaintext credentials and enabling lateral movement. Defending against this requires hardware-level filtering. Enterprise networks combine DHCP snooping, which maps trusted switch ports, with dynamic ARP inspection, which actively cross-references and drops spoofed packets directly inside the switch hardware. Because legacy protocols natively trust any device operating inside the broadcast domain, structural segmentation is insufficient. Securing the modern network requires moving towards strict cryptographic verification. Traditional VLANs are highly successful at mitigating wide-scale congestion, but their security function focuses strictly on traffic moving north-south through a perimeter firewall. They provide zero defense against an infected workstation communicating laterally to another device on the same VLAN. To achieve a true zero-trust architecture, modern data centers are rapidly deploying software-defined micro-segmentation. Instead of tying policies to physical switch ports, fabrics like Cisco SD Access untether security to the software layer. They dynamically inject scalable group tags directly into packet headers, isolating adjacent endpoints unless explicitly permitted by a centralized controller. Concurrently, the transition to the IPv6 addressing architecture introduces a structural shift, the total and absolute elimination of the network broadcast address. IPv6 replaces noisy ARP floods with the optimized neighbor discovery protocol, utilizing precise IPv6 messages. This visual contrasts the two approaches. Instead of blasting a request to everyone, an IPv6 host automatically subscribes to a specific solicited node multicast group based on its unique address. A request is only processed by the mathematically calculated destination. At the hyperscale level, enterprise workloads utilize spine leaf topologies with dense, non-blocking routed cores, removing the structural reliance on the spanning tree protocol. To maintain Layer 2 connectivity across these vast routed fabrics, data centers deploy EVPN and VXLAN overlays. These protocols programmatically distribute MAC reachability information, terminating the bandwidth-heavy flood and learn behavior of legacy switches. Public cloud providers take this even further. The AWS Nitro hypervisor natively strips all Layer 2 broadcast frames before they hit the wire to guarantee tenant isolation and prevent storms. To achieve maximum scale and uncompromised security, the industry had to abandon the foundational concept of a message to everyone. For decades, engineering local area networks meant fighting physical signal overlap with full-duplex switches and compartmentalizing protocol noise with high-speed Layer 3 routers. Yet the persistence of catastrophic bridging loops and trivial ARP spoofing proves that Layer 2 boundaries were structurally fragile once breached. The future of network architecture demands the deprecation of implicit trust and the elimination of unconstrained data flooding. In their place, modern deployments rely on intelligent EVPN control planes, the precision of IPv6 multicast, and software-defined micro-segmentation. The enterprise network boundary has permanently migrated. The perimeter now wraps tightly around the virtual workload